the next topic that we are going to talk about is a very interesting one, and is actually my specialty, and it's about making electromigration-resilient design using computational intelligence algorithms. As technology advances, VLSI circuits are getting smaller, leading to higher current densities. While this allows for greater functionality in smaller spaces, it also introduces, of course, significant reliability challenges. One critical issue, apart from thermal analysis that we just mentioned, is the phenomenon of electromigration, or EM, as we say, where metal atoms migrate under high current densities. Over time, this can create voids and hillocks, which can eventually either break the circuit or cause short circuits, leading to higher drop and signal degradation. Traditionally, designers relied on empirical models to estimate electromigration effects. However, with the increasing complexity of modern circuits, we need more precise, maybe physics-based solutions integrated early in the design flow. And what exactly are the problems with the traditional approaches? In order to explain this, we are going to need to go back to how electromigration assessment is performed inside the interconnects and power grids. For this purpose, we have here Black's model, which calculates the mean time to failure that is caused by electromigration, where it finds the maximum allowed current density, which ensures that the design does not encounter any electromigration problems. Which means that if in a line the current density is over this current density, the maximum current density, then it may experience electromigration issues. So the engineers, layout engineers, sign-off engineers get this information from the design rules and check if the current density of every segment of the circuit does not overpass it. For this purpose, they use tools like Virtuoso Cadence or Totem Red Hawk of ANSYS. In case it does overpass it, they use methods like widening the widths in order to fix it, where EM violations are. But this method has a lot of flaws. And why is that? Actually, the problem lies in two parts. The first one is how we obtain the maximum current density. And the second one is how we optimize the design in order to overcome these issues. In the first part, the academia has already solved this riddle by having widely adopted a physics-based method for electromigration modeling, that is Korhonen's equation. It is a physics-based approach that accurately calculates the stress of due to electromigration instead of providing an imperial rule of thumb that is the mean time to failure by Black's equation. But what about the second problem? How to optimize better to mitigate better the problem of electromigration? And we need to find a more intelligent way to do that. Here is, of course, where computational intelligence comes in. And in particular, a shooting approach is particle swarm optimization. PSO is inspired by the collective behavior of biological swarms, like bird flocks or fish schools. And what exactly is its mechanism is that each particle represents a possible design solution. And it, based on its own best solution that it has seen in the past, and also the global best solution found in the swarm, it adjusts its position. Now, this approach is particularly well suited for problems like ours, like wire sizing in power grids, while keeping area relatively minimal, because it is well suited for high-dimensional and non-linear optimization problems like ours. So the concept is to perform electromigration IR drop optimization on power distribution network lines as a proactive solution, and this is actually becoming quite crucial as the technologies shrink. In particular, the proposed method takes as inputs the power grid characteristics, the current densities, and the design constraints, and as output, it provides optimized wire sizes to balance reliability and area efficiency. This method is suggested to be integrated after place and route, where all power needs and geometry of the power grid have been determined. And by integrating this into early sign-off steps, we can proactively improve circuit reliability before fabrication. This reduces design iterations, minimize last-minute fixes, which of course cannot do much, and ensures a more robust final product. But in order to scale this approach for future technology nodes, we need to focus on 3 key areas. The first one is scalability, of course, in a way that as circuits become denser and more complex, our optimization methods must adapt to handle even larger power grids efficiently. Once again, in order to create efficient machine learning methods for this purpose, there is a need to develop standardized datasets and benchmarks for EM-aware optimization, the very large problem that EDA community has, not enough free data. Another important step is industry adoption. While research has demonstrated the effectiveness of computational intelligence for electromigration resilience, these techniques need to be integrated into existing EDA tools. By developing user-friendly plugins in already existing tools like Virtuoso and other from ANSYS that work within the standard design flow. And of course, standardizing these methodologies will also encourage their adoption in early design phases rather than relying on last-minute fixes. And finally, and most importantly, I would say, is interdisciplinary collaboration. It is essential as we need to foster strong partnerships between academia, industry, and AI experts in order to push this research forward. And by bringing this together, these diverse fields, we can develop more intelligent, automated design strategies that not only improve circuit reliability, but also enhance the overall efficiency of the VLSI design process. So to conclude, by integrating intelligent optimization early in the design process, we can ensure more reliable and more efficient circuits for the technologies of tomorrow, as the technologies are shrinking and shrinking time to time, day to day, and they are becoming more complex.